This tutorial describes the operation of the laboratory heat pump instrument ET102, which is utilized to understand the thermodynamic cycle of a heat pump. Recording and displaying data is recorded in the software housed in the computer next to the device. Heat pumps and refrigerators are devices that use mechanical work to transfer or pump thermal energy from a low temperature space to a high temperature space. Refrigerators and heat pumps are the same devices, but they have different objectives, and we have all seen them. A heat pump's goal is to maintain a space's temperature above the temperature of the surroundings, whereas a refrigerator's goal is to maintain a cold space below the temperature of the surroundings. The most common heat pump thermodynamic cycle is the vapor compression cycle. This activity aims to learn about the functionality of a heat pump using the device ET102. The objective of this lab section is to understand the thermodynamic cycle of a heat pump and a refrigerator, utilize pressure enthalpy diagrams, understand and calculate refrigerant properties and coefficients of performance, and draw engineering-based comparisons between the values ideal, real, and experimental coefficient of performance. The device ET102 is a heat pump that uses the refrigerant R513A. This device is composed of two major systems, including the heat pump and an external water circuit that takes the thermal energy from the heat pump. Both systems will be described next. The heat pump uses a vapor compression cycle with the refrigerant R513A. The main components of the heat pump are: the compressor circulates the refrigerant and increases its pressure and temperature before entering the condenser. The condenser. The refrigerant condenses as it releases thermal energy to the hotter space or surroundings. The expansion valves allow the expansion of the refrigerant, decreasing its temperature and pressure before entering the evaporator. The evaporator. Here the refrigerant evaporates as it takes thermal energy from the cooler space. The low pressure section of the heat pump is insulated in black, whereas the high pressure section is colored with red. Other components that are part of the device ET102 include the main switch to turn on the device, switches for compressor, the fan, and the pump, displays of temperature, pressure, electric power, and water flow rate. Knowledge of the refrigerant temperatures and pressures at various locations along the thermodynamic cycle will allow the students to calculate the ideal and real coefficients of performance, or COP. For this, the pH diagram of the R513A refrigerant will be utilized. The COP is defined as the ratio of the amount of energy discharged to the hot body from the system undergoing the cycle to the network into the system to accomplish this effect. The second system of the device ET102 is the external water circuit. The goal of this system is to take the thermal energy from the heat pump's condenser to heat up water. The external water circuit allows students to calculate the experimental coefficient of performance. The water circuit is composed of a heat exchanger pipe that runs internally and coaxially through the heat pump's condenser tubing. The water runs in opposite directions with respect to the refrigerant flow, that is, in a counterflow configuration. The hot water line is green. A pump circulates the water along the green pipes. The volumetric flow is adjusted by the black control valve knob and displayed on the left display panel. Once the water has absorbed thermal energy or heat from the heat pump's condenser, it enters a second heat exchanger. Within this tank, the hot water that runs through the green pipes exchanges heat with cold water that comes from the building's HVAC system. This cold water runs through the blue pipes. Knowledge of the volumetric flow and the inlet and outlet hot water temperatures running through the green line will allow the students to calculate the experimental COP. In this video, we are going to describe an experiment where the water flow rate of the external water circuit is set to 20 liters per hour. Note that additional flow rate values can be required for other laboratory activities. Refer to the laboratory guide for specific details. Before operating the machine, make sure to wear safety goggles and adhere to the laboratory safety rules. Take note that all preliminary measures have been completed. Check the storage tank is filled with water to a visible level. Open all external coolant lines as directed. At this point, we are ready to turn on the device. First, turn on the computer located to the left of the heat pump and log in using your University of Arizona NetID. Take note that all preliminary measures have been completed. Turn on the heat pump by rotating the main switch. Note that the displays will turn on and begin displaying data. Open the software ET102 on the desktop. Ensure that the Hide Values option is not selected. Identify the compressor and evaporator fan switches. Push both switches up simultaneously to turn the compressor and the evaporator's fan on. Students should begin to hear the fan spinning. Turn the rightmost switch on to activate the water pump. Water should start flowing through the external water circuit and the flow magnitude should appear on the water flow display. Wait 1 minute for the system to stabilize. Using the black control valve knob located on the right of the machine, adjust the hot water flow rate to the stated value, in this case 20 liters per hour. Adjust in small increments as this control valve is sensitive. All the sensor information is being displayed on the device's software. To record the data, open Data Logger and begin measurement. Open the chart recorder window to view the data. Open the log pH diagram window. The thermodynamic cycle will appear in blue on the graph, where the thermodynamic state changes as a function of time. Students should wait at least 60 minutes before ending the experiment and saving the data. At this time, students should save the data acquired by the ET102 software. Stop recording data in the software by selecting Pause on the chart recorder, and then export the data and save as a .txt file to the student's preferred folder. Exit the software. Once the experiment has been completed, verify the data has been saved and begin to properly shut off the machine. Turn off the pump, turn off the compressor, turn off the evaporator fans, and finally turn off the main switch. Wait 5 minutes before turning off external cold water valves, allowing the machine to properly cool.